Thanks to CuriosityStream for supporting PBS Digital Studios. Imagine an enormous rainforest teeming with life, trees, insects, pretty little birds. Primates are climbing up in the canopy while crocodiles and turtles swim in the rivers below. Beautiful, isn't it? Now imagine this lush rainforest in the Arctic. There was a time not too long ago when the world warmed more than any human has ever seen. So far. This ancient warming took place over the course of just 200,000 years, the blink of an eye in geologic time, and it ended much like it began, suddenly and mysteriously. It all started 56 million years ago at the very end of the Paleocene epoch. Back then, life was still recovering from all the unpleasantness of the Cretaceous-Paleogene extinction event, which wiped out the non-avian dinosaurs, and things were already warm by today's standards. There were no polar ice caps, which meant sea levels were much higher, and the continents, which were just beginning to take a familiar shape, were covered in habitats like temperate forests and deserts, and a belt of rainforests around the equator. But this environment was about to change. In fewer than 20,000 years, the global average temperature increased by 5 to 8 degrees Celsius, and the warming was greatest at higher latitudes. So at the poles, temperatures on land reached an average of 23 degrees Celsius, while the ocean waters got up to a balmy 20 degrees. This means you could have gone for a comfy swim in the seas around Antarctica. This remarkable and sudden warming event is known as the Paleocene-Eocene Thermal Maximum, or PETM, and it had a massive effect on life on Earth. For one thing, when the PETM reached its peak, rainforests had expanded much farther than they ever had before. Fossils from North America, Europe, and Asia reveal habitats rich in plant life that are today associated with tropical rainforests, even though these forests were nowhere near the tropics. The fossilized fronds of palm trees have been found as far north as Wyoming, for example, and some places within the Arctic Circle, like Ellesmere Island in Canada, show evidence of ferns, redwoods, and ginkgos. So, how was any of this possible? Our best clues can be found in ancient sediments. Marine sediment samples from Maryland to Antarctica show that about 56 million years ago, there was a sudden spike in the amount of carbon dioxide and other greenhouse gases in the oceans. And judging by the types of carbon found in these sediments, these gases likely came from organic matter, like plants. See, plants, like most living things, prefer to use the lighter and more common isotope of carbon, carbon-12, as opposed to the heavier isotopes like carbon-13. So this biogenic carbon, which we've talked about before, has a different chemical signature than carbon that's never been part of a living organism. And sediments that date to the start of the PETM show a large and sudden drop in the ratio of carbon-13 compared to carbon-12. This means that a bunch of biogenic carbon must have suddenly been released into the atmosphere in the form of carbon dioxide, methane, and other gases. But where did these gases come from? Well, one hypothesis is that there was a rash of massive wildfires that unleashed tons of CO2 that had been locked up in plants. Another model proposes that giant seams of coal were exposed to the heat of volcanic activity, which would have released the carbon from fossilized plants. Or it could be that an otherwise mild warming event triggered the release of greenhouse gases by melting deposits of a compound known as methane hydrate. Methane hydrate is similar to ice, but it contains molecules of methane trapped by molecules of water. And hydrates are usually stable as long as they're kept under a lot of pressure, like deep in the oceans, or if they're kept cold, like in permafrost, the thick layer of frozen soil that forms in cold climates. But if these places warm up, the hydrates melt, releasing bursts of methane, which is an even more potent greenhouse gas than CO2. And of course, the more warming that happens, the more melting there is, which releases even more greenhouse gases, creating a classic positive feedback loop. Now, no matter how it started, it's worth noting that during the PETM, carbon was released into the atmosphere at only a fraction of the rate at which it's being emitted today. One study of marine sediments from the Arctic showed that at the peak of the PETM, as much as 1.7 billion metric tons of carbon were released into the atmosphere every year for at least 4,000 years. A similar study of sediments from New Jersey puts the figure at about 1.1 billion tons of carbon every year. Now, compare that to the amount of carbon that's being released today. In 2014 alone, it was 9.8 billion metric tons of carbon. So 56 million years ago, carbon was being released less quickly than it is now, but those emissions continued for thousands of years, and it was more than enough to create a potent greenhouse effect. With more carbon in the atmosphere than plants could absorb, the planet started to change rapidly. In many places, the climate delivered a combination of humidity and heat that allowed vast rainforests to flourish, and among the animals that thrived in these warm forests were reptiles. Fossils of alligators, crocodiles, and turtles can be found in nearly every fossil bed from the PETM, even in the polar forests of Canada and Greenland. And these lush forests were also where many early mammal groups diversified, including our very own lineage, the primates. In fact, the earliest true primates appear in the fossil records just as the PETM was starting to take off 56 million years ago. They adapted quickly to a world covered in trees, developing things like forward-facing eyes, fingernails instead of claws, and opposable thumbs. These features gave primates such an edge that by 53 million years ago they could be found all across the northern hemisphere, from tiny Eosimius in China to Nearcticus in Wyoming. But in the oceans, life in hothouse Earth became much harder. In fact, in some places it was almost impossible. At the equator, ocean temperatures were unbearably hot, sometimes reaching as high as 36 degrees, almost as hot as your average hot tub. This was probably too hot for many kinds of plankton, which were and are the basis for most ocean food webs. But an even more devastating side effect of high CO2 levels was ocean acidification. When ocean water absorbs CO2, it becomes more acidic, and this in turn depletes water's concentration of carbonates, the compounds that many organisms use to build shells and other structures. And this is why one of the clearest effects of the thermal maximum can still be found in core samples from the deep sea. Sediments that date back to before the warming are typically pale in color because they're rich with the skeletons of deep sea foraminifera. Also known as forams, these are tiny protozoans that build shells out of calcium carbonate. And where forams were abundant, the chalky fossils of their shells turned the ocean bed white. But when the oceans became more acidic, the sediments turned dark because most of the forams just disappeared. During the PETM, between 30 and 50% of all foram species went extinct. The same phenomenon also stunted the growth of hard corals, which need carbonates to build their skeletons too. So during the PETM and for millions of years afterward, big complex coral reefs all but disappeared from the fossil record. All told, the thermal maximum was a mixed bag for life on Earth, proving to be an important period for us mammals, but a major loss for some marine life. And like all dramatic events, the PETM did come to an end, although we're not sure how or why. Over the course of the Eocene epoch, the climate slowly began to cool, and although the temperature occasionally spiked again, it never reached the extremes of the maximum. Temperatures kept dropping during the Eocene, so much so, in fact, that by the end of the epoch 34 million years ago, polar ice caps had begun to form. But how did we get from rainforests near the poles to ice caps? Well, the cause of the initial cooling that actually stopped the PETM 53 million years ago remains a mystery. But something allowed that cooling to take hold and make the world even colder. And the answer here might have to do again with plants. Arctic sediments that date back to the early Eocene, 49 million years ago, have been found to contain huge swaths of fossilized aquatic ferns known as azala. These plants thrived in the lush, warm Arctic, but as the environment changed, they died off, and as they dropped to the seafloor, the thinking goes that they took tons of carbon with them, which caused temperatures to drop even further. Despite how little we know about its end or its beginning, the Paleocene-Eocene thermal maximum shows us just how polarizing climate change can be for life on Earth. For some organisms, like early primates, the warming was a chance to develop new forms and spread to new locations. But for corals, forams, and other marine life, such extreme heat and carbon concentrations spelled disaster. It gives us, in the midst of our own period of warming, a view of how extreme the effects of climate change can be. And it allows us to make some pretty striking comparisons. Remember when I said that during the PETM the globe warmed more than humans had seen so far? Well, keep in mind that in recent years the rate of annual carbon emissions have been more than 5 times greater than they were at the peak of the PETM. As a result, our world is warming faster than it did back in the Eocene. Just over the past 100 years, the average global temperature has increased by about 0.7 degrees Celsius. And that's just been over the past century. During the PETM, it took perhaps thousands of years for temperatures to rise that much. So the PETM is the closest we can get to understanding the effects of global warming today, and it has a lot to teach us about the extremes that life experienced both on land and in the seas. Yes, rainforests full of primates and insects and reptiles are beautiful, but I think you'll agree with me that most of us like them to stay where they are today. PBS Digital Studios is sponsored by CuriosityStream, where you can stream documentary films and programs about science, nature, and history, including exclusive originals. For example, check out Rise of the Continents, a BBC series that uses geological clues to recreate the supercontinent of Pangaea. CuriosityStream offers unlimited streaming, and for you Eons viewers, the first 2 months are free if you sign up at curiositystream.com/eons and use the promo code EONS. All right, we need your help. What do you want to know about the story of life on Earth? Let us know in the comments, and don't forget to go to youtube.com/eons and subscribe. If you like this episode, you can share it with people who you think might also enjoy it, because look, it's fascinating stuff. And now, do yourself a favor and check out some of our sister channels from PBS Digital Studios. Your brain will thank you.